This chart breaks down the $93 billion NASA spent over 13 years trying to return astronauts to the Moon. These allocations poured into massive hardware programs like the SLS rocket, the Lunar Gateway space station, and 2 different lunar landers. Tracking those expenditures across a timeline reveals a disconnect between public promises and technical reality. While 2024 was the stated goal, internal feasibility data leaked in late 2025 indicated that a crewed landing would not happen until September 2028 at the earliest. One of the primary bottlenecks involved the vehicle designed to carry astronauts to the surface. SpaceX's Starship development track showed 5 failures out of its first 11 test flights. Before that ship could attempt a crewed mission, it had to demonstrate orbital refueling. A single moon-bound Starship requires up to 16 separate fuel tanker launches to fill its tanks in space, a feat of orbital logistics that had never been attempted. NASA remained caught in a loop. The agency continued to fund upgrades for legacy rocket hardware, while ignoring the data that suggested the current path was mathematically impossible. In February 2026, Jared Isaacman took over as the new NASA administrator. He entered the office as a billionaire tech entrepreneur who had already led a private SpaceX mission and conducted his own spacewalk. Having floated in the vacuum of space himself, Isaacman applied a focus to the performance data that previous leadership appeared to be ignoring. 3 weeks into his tenure, at an event called Ignition Day, Isaacman executed the most significant pivot in the agency's history. He suspended work on the $5.3 billion Lunar Gateway and halted construction of an upgraded SLS rocket and a $2.5 billion launch pad in Florida. This decision immediately impacted the global space community. International partners in Europe, agencies in Japan and Canada, and the UAE suddenly saw years of committed engineering work thrown into uncertainty. Isaacman argued that continuing to fund the existing architecture was a choice to ignore the failure rates. To ensure a human return to the Moon, the agency had to stop subsidizing outdated plans and build a realistic path to victory. The first step in that new path involved redesigning the Artemis 3 mission. Originally planned as a lunar landing, it is now a 30-day Earth orbit test flight scheduled for mid-2027, focused entirely on proving the Orion spacecraft can dock with a lander in space. This pivot follows the methodical logic of the 1960s. Before the historic Apollo 11 journey, Apollo 9 conducted the same high-stakes docking tests right in Earth's orbit. These orbital tests serve as the prerequisite for Artemis 4. Now targeted for early 2028, this mission will carry 4 astronauts to the Moon, with 2 landing near the South Pole while the others remain in orbit. Success would mark the first human footprints in the lunar dust since December 1972. In the 55 years since humans last walked on the Moon, the world has been transformed by the internet, smartphones, and global connectivity. Artemis 4 will fly with 4 engines originally used on the space shuttles. It will be the final flight for these legendary pieces of hardware. By returning to a step-by-step testing phase, NASA prioritized a reliable mission profile over the public pressure to launch sooner. To solve the lander problem, Isaacman pitted SpaceX and Blue Origin against each other. Whichever company delivers a lunar-capable spacecraft first is the one NASA will use. SpaceX is offering the Starship, a stainless steel vehicle as tall as a 15-story building that requires an internal elevator to descend to the lunar surface. Blue Origin's Blue Moon lander takes a different approach. Standing at 1/3 the height of Starship, it relies on a traditional staircase and represents a massive independent investment in lunar hardware. The astronauts will explore the surface in suits designed in partnership with the fashion house Prada. These suits feature 4G connectivity, HD cameras, and biometric monitoring, and are engineered to fit any body size. They will be joined by a fully autonomous rover, the first of its kind. When no astronauts are present, this vehicle navigates the surface independently, gathering data around the clock. Shifting the pressure of lander development to the private sector created a corporate race designed to overcome engineering bottlenecks through competition. The target landing site is the Moon's South Pole, specifically craters that have remained in total darkness for approximately 2 billion years. While Apollo 11 spent 21 hours on the Moon, the Artemis 4 crew will stay for a full week. Over approximately 170 hours, they will conduct 6 separate surface excursions. They will deploy seismometers to measure moonquakes and an experiment called LEAF, which studies how plants grow under lunar gravity. Their primary objective is the search for subsurface ice. Finding and extracting this frozen water provides the drinking water and oxygen necessary to sustain a human presence beyond Earth's orbit. These instruments move the mission beyond symbolic exploration toward the active prospecting of the moon's physical and economic resources. This chart shows how lunar ice can be converted into liquid hydrogen and oxygen. Manufacturing rocket fuel directly on the moon changes the economics of deep space travel, as ships would no longer need to carry every drop of fuel from Earth. Geopolitical pressure adds a sense of urgency to this effort. China is advancing towards its own lunar landing target of 2030, transforming the Artemis program into a race for long-term presence. NASA's current vision includes a habitable base camp by 2036, a facility capable of producing its own oxygen and fuel from local materials. The Apollo missions mirrored a camping trip: arrive, explore briefly, and leave. The restructured Artemis architecture focuses on the destination, a permanent expansion of human civilization to the moon and beyond.